Hi everyone, I am Anthony Usha, Assistant Professor from the Department of Aeronautical Engineering in Gojan School of Business and Technology. We are going to discuss about the topic Performance and Propulsion from the Unit 3. In this unit, we will explore the exciting dynamics that power the vehicles, aircraft and spacecraft. Let's dive into this. Unit 3 Performance and Propulsion. We will begin by examining the key factors that affect performance, such as thrust, drag, weight, and lift. Here, the syllabus goes like viscous and pressure drag, flow separation, aerodynamic drag, thrust calculation, thrust of power available, and thrust power required. And here we are going to learn about the forces which interact with the engineering, how it balances and to get the optimize the speed, maneuverability and fuel efficiency. So by this end of the unit, you will have a solid understanding of both the science and engineering behind motion and how performance and propulsions are crucial in designing modern vehicles. Some of the few important topics from the Unit 3 propulsion and its performance are viscous and pressure drag flow separation, components of aerodynamic drag acting on the aircraft, thrust generation in a jet engine, power available and power required are determined by forces which are acting on an aircraft and thrust calculations. Aerodynamic drag. Aerodynamic drag is a resistance of an object which faces it moves through air. Here, what type of drag is affecting the object? They are viscous drag and pressure drag on common. The viscous drags which arises from the fluid's viscosity and the surface friction, whereas the pressure drag which result from pressure differences around the object. The engineers works to minimize drag through sleek designs and smart materials. Reducing the drag means faster, smoother and more efficient flight. So we are working on it. Aerodynamic drag. Aerodynamic drag. The total force opposing motion. Viscous drag. Friction caused by the fluid's viscosity. Pressure drag. Force arising from pressure differences across the body. Whereas in aerodynamic drag, it is the total force that resists the motion of an object through a fluid like air. This force acts opposite to the direction of movement, slowing the object down. Viscous drag. This type of drag is caused by the friction between the object surface and the fluid. It occurs due to the viscosity or thickness of the fluid and affects how smoothly the object moves through it. Pressure drag. This drag results from the difference in pressure between the front and rear of a moving object. As the object pushes through the fluid, a low pressure region forms behind it, which creates a backward pull, which causes the flight moves forward. Viscous drag. Let me discuss what is viscous drag in detail. I have shown a flow chart of a viscous drag from the end to end. That is the fluid, air, surface of moving body, friction and the cause of viscous drag and to end of shear stress. Here, as the fluid flows over the surface of the body, it sticks to it, creating a shear stress. This stress results in energy loss, which we recognize as a viscous drag. The diagram shows two types of surfaces. On the left, a smooth surface leads to laminar flow, but causes a large amount of flow separation behind the object. On the right, a dimpled surface promotes the turbulent flow, which reduces separation and surprisingly lowers the overall drag. Characteristics of viscous drag. Let's look at the main factors which influence the viscous drag. Firstly, the boundary layer. This is the thin region where the surface which is near to this fluid velocity which changes from 0 to the free stream velocity, and it is the main zone where viscous effects are significant. Secondly, surface roughness. Any roughness or texture on the surface which disrupts smooth flow, increasing the friction and drag. Third, viscous drag itself. This is the central force resisting the motion of objects to the fluid and which caused by the internal friction between the fluid layers. And finally the Reynolds number. The Reynolds number which helps to characterize the flow whether it is laminar or turbulent and influence how much viscous drags will be experienced. Together these factors define how a fluid behaves near surfaces and how efficiently objects move through it. Pressure drag factors. Pressure drag is a major component of total aerodynamic drag and which is influenced by three key factors. First, high pressure region, flow separation, and the third is dependence on shape. First, the high pressure region at the front of a moving object, air piles up and creates a high pressure zone. This pressure resists motion and contributes significantly to drag. And second, flow separation. As the air flows around the object, it may separate from the surface, forming turbulent eddies and a low pressure wake behind the object. This increases drag dramatically. Third, dependence on shape. A blunt body causes more disturbance in airflow, leading to higher drag. In contrast, streamlined shapes allow air to flow smoothly, reducing the pressure differences and minimizing the drag. Understanding these factors help engineers design more efficient and aerodynamic vehicles and structures. Characteristics of pressure drag. Pressure drag occurs due to the difference in pressure between the front and the rear portion of a moving object. The diagram depicts at the front the airflow stagnates, creating a high pressure region. This pressure pushes against the object, contributes to drag. As the air flow around the object, it separates at the rear, forming a low pressure region and a turbulent wake. This wake creates suctions that push the object backward, which increase the drag. The cross-sectional area faces the flow determine how much pressure is in front and the low pressure behind. This result in the large resistance will create. Finally, the resultant pressure force is the net effect of high pressure in front and low pressure behind, pushes the backward. Drag coefficient. The drag coefficient is a dimensionless number that quantifies the drag forces on an object as it moves through the fluid. Let's look at three cases shown in the slide. In the first image, we see a blunt object with the significant friction and pressure acting on its surface. The flow remains attached or a short distance and quickly separates, leading to high drag. In the second image, the flow separates early behind the circular object. This results in a large wake with turbulent, low pressure regions and high energy loss causes a high drag coefficient. In contrast, the third image shows a streamlined shape. Here the flow stays attached over the movement of the surface, that is more of the surface. This allows pressure recovery at the rear, reducing the size of the wake and significantly lowering the drag. Thus, the drag coefficient depends on the shape of the object, the smoothness of the flow, and how well pressure is recovered behind the body. Flow separation and its stall. This diagram explains what is flow separation over an airfoil, a key factor in understanding the aerodynamic stall. At the front of the airfoil, the air meets the surface at the stagnation point where the flow velocity is zero. As the air moves along the surface, it first experiences a laminar boundary layer which is smooth and orderly. Further downstream, This laminar flow transition into a turbulent boundary layer which has more energy and can resist separation longer. Eventually, the flow may no longer follow the surface counter, leading to the flow separation. This occurs at the separation point, typically on the upper surface. Beyond this point, a turbulent wake forms, causing a sudden loss of lift and increase in drag. This condition is known as aerodynamic stall. Managing the boundary layer and delaying the separation is essential for maintaining stable and efficient flight. This diagram shows how airfoil behavior changes with increasing angle of attack. At 0 degrees, the airfoil is smooth with a small turbulent wake behind the trailing edge, which is the lift is generated efficiently and the drag is minimal. At 5 degrees, the separation point moves slightly forward. That is, the lift increases as more air is redirected downward, but the wake also grows. At 16 degrees, the airfoil reaches its stall angle where the maximum lift is produced. Beyond this point, the separation point jumps forward rapidly. At 20 degrees, the airflow is almost fully separated, forming a large turbulent wake. This significantly reduces lift and greatly increases the pressure drag. This sudden loss in lift is what we call a stall, a critical concept in aircraft performance and safety. Reynolds number. Reynolds number is a dimensionless quantity that helps us predict how to flow behavior, whether it will be smooth or chaotic. At low Reynolds number, the flow around a border is laminar, smooth and orderly. This occurs in slow moving or highly viscous flow. As Reynolds numbers increases, we enter the transitional regime. Flow begins to show sign of instability and small eddies start to form. At high Reynolds number, the flow becomes a turbulent with random chaotic fluctuations and swirling vortices. This is common in high speed or low viscosity environments. Understanding Reynolds number is crucial in aerodynamics and flow mechanics as it governs drag, lift and flow separation. Breaking down aircraft drag. When an aircraft moves through the air, it experiences resistance. This is called drag. Aircraft drag is broadly classified into two types, parasite drag and induced drag. Parasite drag occurs due to the aircraft intention with the air and is made up of three components which are form drag, caused by the aircraft shape. Think of the resistance from the aircraft body obstructing the airflow. Skin friction drag, which is created by the air rubbing against the surface of the aircraft. Smoother surface reduces the type of drag. Interference drag, which arises where different components meet, such as the wing and fuselage junction, disturbing the airflow. Induced drag, on the other hand, is directly related to lift. It forms as a byproduct of the pressure difference above and below the wings. Interestingly, induced drag decreases as airspeed increases while parasite drag increases with the speed. So understanding these types of drag helps engineer and pilot minimize the fuel usage and enhance aircraft efficiency. Drag coefficient. Drag coefficient is also can be mentioned as CD, which is a dimensionless parameter that quantifies the drag force relative to the fluid density, velocity, and reference area of the object, which is used to compare the aerodynamic efficiency of different shapes and designs. Lower the CD values will indicate more aerodynamically efficient shapes. The formula for drag coefficient is half rho v square ACF. Rho is air density, v is the velocity, a is the wetted surface area, and c is the skin friction coefficient, and the df is skin friction drags. Applications of drag in marine engineering, wind energy, aircraft design, and automotive industry. Not only in aircraft design, we are seeing that drag plays in varying role in engineering era. Marine engineering, which reduces the drag on ship hulls, improves speed and fuel efficiency. The maneuverability is also improved. Wind energy, which minimizes the drag on turbine blades, which enhances the energy capture. Streamlined design also optimizes the performance. As we know in aircraft design, reducing drag improves aircraft fuel efficiency and speed. Also, the streamlined shapes contribute to better performance. In automotive industry, the aerodynamic drag impacts fuel efficiency and vehicles performance. Smooth contours and spoilers help reduce drag. Thrust generation in a jet engine. Thrust is the forward force which is exerted by a propulsion system to move a vehicle forward. It is generated by accelerating a mass of fluid such as air or exhausted gases in the opposite direction, which is the forward force that powers a jet to the sky. It is created by the accelerating air. Thrust generation in a jet engine. This reaction force is as per Newton's third law, which propels the engine and the aircraft forward with power and precision. Thrust in a jet engine is generated based on Newton's third law of motion. For every action, there is an equal and opposite reaction, which is a famous quote which propels the aircraft moves forward. Let me discuss the basic steps in a jet engines that creates the thrust generation. Air enters through the front intake and is compressed by a series of rotating blades. This compressed air is then mixed with fuel in the combustion chamber. The fuel air mixture is generated and ignited, which produce a high temperature, high pressure gas. This gas rushes through the turbine blades, causing them to spin and drive the compressor. Finally, the gases inside are exhausted and expelled at high speeds through the exhaust nozzle. According to the Newton's third law, this backward jet of gas pushes the aircraft forward, the generating thrust. Jet engine types: piston engine, the rotary engines, rocket engines, turboprops, turbofans, and turbojets. These are all types of the aircraft propulsion systems. Each serves as a unique role, from slow to speed, general aviation to high-speed space missions. The engine type defines the performance, efficiency, and the aircraft mission capability. Each engine type operates on a unique principle. Piston and rotary engine convert combustion into mechanical rotation. Turboprops and turbofans use turbine to drive. Propellers or fans for thrust. Turbojets and rocket generate direct thrust by accelerating high-speed exhaust gases. Each design serves as a specific flight needed. Engine types. In the world of jet propulsion, understanding each type is essential to appreciating the balance between speed, efficiency, and functionality. Let's explore four main types of jet engines: turbojet, turbofan, turboshaft, and turboprop. First, the turbojet engine. This is the simplest form of turbojet engine and is primarily designed for high-speed aircraft. Air enters through the intake and is compressed. The compressed air moves into the combustion chamber where fuel is added and ignited. The resulting high temperature exhaust gas expanded through a turbine, powering the compressor and the exhaust nozzle, which produce the thrust. Turbojets are highly efficient at supersonic speeds, but less at lower speed or altitudes. Next, we move to the turbofan engine. This is the mostly common used engine in modern commercial aviation. In a turbofan, a large ducted fan at the front pulls in more air. A portion of this air enters the core, like in a turbojet, but most bypass the core and is accelerated by the fan. This bypass air generates additional thrust, making turbofan more efficient and quieter than turbojets, especially at subsonic speeds. The turbo shaft engine is commonly found in a helicopter and some naval vessels. Similarly, in core design into a turbojet, the turbo shaft redirects most of its energy not into producing thrust but into driving a power shaft connected to a rotor or gearbox. The exhaust still exists to the nozzle, but the thrust is minimal compared to the shaft output. This makes the turbo shaft ideal for mechanical power delivery rather than propulsion. Finally, the turboprop engine, not only shown in the specific diagram, operates similarly to a turboshaft but uses the shaft power to drive a large external propeller. These engines are typically used in small regional aircraft and provide excellent fuel efficiency at lower speeds and altitudes. Each of these engines are evolved to serve specific aviation needs, from breaking the sound barrier to lifting off vertically or cruising efficiently. Jet engine working principle. This diagram represents the basic thrust generation mechanism of a jet engine using the principle of momentum conservation. Air enters into the engine at a velocity denoted by V infinity or free stream velocity, shown here on the left in blue arrows. This is the aircraft's speed through the air. Fuel is then injected into the engine and combusted. The combustion process adds significantly energy to the air, increases its temperature and pressure. As a result, air is expelled at a much higher speed, labeled as Vj or jet velocity, indicated on the right side by orange arrows. The difference between the inlet velocity and the jet velocity creates a net charge in momentum. This change in momentum produces a reaction force, which we perceive as a thrust, pushing the aircraft forward. This is governed by Newton's second and third law of motion. The thrust force can be mathematically expressed as thrust equals the mass flow rate multiplied by the difference in jet and inlet velocities. This diagram also shows the fuel being added to the system and energy lost as heat and other inefficiencies are marked in red. This simpler flow diagram helps us understand how jet engine converts chemical energy into the kinetic energy to propel the aircraft forward with incredible efficiency. Engine type comparisons. Jet engines are the heart of modern aviation, powering everything from commercial airliners to cutting-edge military aircraft. Let's explore the main types of jet engines and how they work. Engine types: turbojet, turbofan, turboprop, turboshaft, ramjet, and scramjet. And what are the comparisons have made is fans of propeller, speed range, and common usage. In a turbojet, there is no fan or propeller, and with the speed range is about high to supersonic, and the common usage is in fighter jets or Concorde. In turbofan, there is a fan to produce the thrust, and the speed range is about subsonic to transonic, and the common usage is commercial airliners. In turboprop, there is a propeller to produce the thrust, and the speed range is low to medium, which is used in regional aircraft or cargo planes. Turboshaft. there is a shaft to generate the thrust, and the speed range is not is based on the thrust which is produced, and it is a commonly used in helicopter marines and the ramjet. The speed range is supersonic. The common usage is in missiles, high speed aircraft. The scramjet, there is no propeller or fan which is used, and for both the ramjet 2, and here the speed range is hypersonic, and which is used in space research and weapons. Comparing the jet engine and rocket engine performance. Jet engines and rocket engines both generate thrust, but they operate in fundamentally different ways and are built for very different environments, right? So jet engines or air breathing engines, they intake atmospheric air, compress it, right? So whereas in rocket, they rely on the atmosphere, and the rocket carry both fuel and oxidizer, which means they can operate in the vacuum of space. They burn the propellants in a combustion chamber and expel at high speed to generate the thrust, which is based on the Newton's third law of motion. And although rockets are less efficient in atmosphere, they provide much higher thrust, and which is ideal, which the launching payloads into orbit or deep space missions. Whereas the key comparisons I have made is working medium, like jet use atmospheric air, rocket can carry their own oxidizer. In environments, jet works only within the atmosphere, whereas in rockets can carry in space. Efficiency. Jets are more efficient at subsonic speed. Rockets are more better for space and extremely high speeds. Speed. Jet engines power aircraft up to Mach number 3, and rockets can exceed Mach up to 20. Endurance. Jet can operate for hours, and rocket burn fuel rapidly and operate for minutes. Hence, jet engines are optimized for atmospheric flight, while the rocket engines are built to conquer the vacuum of space. So each plays a vital role in modern aerospace technology. Power available from propulsion systems. When analyzing aircraft performance, it's important to understand power available, or P, which represent how much useful the power engine which delivers for forward motions, right? So for a jet engine, the power available is directly related to thrust and aircraft velocity. So it is calculated by using the formula power available is equal to force into V, that which is the product of force and velocity, where the F is the thrust produced by the engine and V is the velocity of the aircraft. So as the aircraft goes faster, the power available also increases. So propeller engine which drive on the aircraft, the concept is a little different. Here the power available depends on the engine's output power, which is adjusted by how efficiently the propeller converts the power into thrust, which is given by the efficiency into bhp, that is the brake horsepower of the engine. So PA is equal to eta, that is the propeller efficiency into bhp. The propeller efficiency accounts for how well the spinning propeller turns engine power into thrust. Jet engine thrust directly, and power increases with speed. In propeller engine rely on rational power, and which is limited by propeller efficiency. Power available from propulsion systems. This graph illustrates the relationship between the power setting and the airspeed, a crucial concept in aircraft performance and flight safety. The upward curving blue line is represent the power required to maintain the steady level flight at the different speeds. Notice that it forms a U shape. The lowest point on this curve corresponds to the minimum power required. That is the speed where the aircraft flies most efficiently. Now the green line above shows the maximum power available from the engine at various speed. The excess power, the difference between the two curves, is what allows for climbing or accelerating. To the left of the minimum power point lies a shaded gray region, labeled the region of reverse command. This is where slow flight occurs. In this region, the aircraft requires more power to fly slower, which seems counterintuitive. Power required versus power available. This diagram shows the relationship between thrust required, thrust available, and the true speed through airspeed for an aircraft operating at a constant density altitude. The red curve represents the thrust required for steady level flight at two different payload weights, in solid for maximum payload and dashed for 50% payload. As speed increases, the thrust required initially decreases, reaches a minimum and then rises again due to drag increases with speed. The blue lines shows thrust available from the engines, one for wide open throttle and another for 85% throttle. The aircraft can only maintain level flight where the available thrust meets or exceeds the required thrust. Points A and B represent the operating point for maximum load at 85% throttle. The aircraft can fly between these two speeds outside his range. Either the engine power is insufficient or the aircraft stalls. Point C and D shows the wide range available when payload is reduced to 50%. The required thrust curve shifted downward, allowing the flight to higher speeds with less engine effort. The shaded region to the left marks the stall or buffer boundary where flying becomes aerodynamically unstable due to the loss of lift. This chart is critically for pilots and engineers to determine safe and efficient operating speeds, ensuring that the aircraft remains within the envelope of available thrust at various load conditions. Factors which affects the thrust and power requirements. Higher thrust and power requirements, which are wing configurations, changes in wing shapes, influences on drag coefficient, the aircraft weight, higher induced drag, increased lift requirements, reduced engine performance, decreased air density and altitudes. So these are the key factors which affects the thrust and power requirements. I have basically divided the key points based on their components and based on the relevant figures. Thanks for watching.